Let's talk about the unordered priority queue. So we'll create a priority queue and we'll have an implementation that falls back to using an unordered collection. So by that I mean that the items will be stored in no particular order. In this case we'll actually be a little bit more precise. We'll look at using a linked list. This could also be done with an array list, so that's left as an exercise for you to consider, but this example will review using a linked list. So let's look at our four fundamental operations. The insert operation is basically appending a new item to the list. Extracting the minimum item is going to be a little bit more complicated. We'll have to find where that minimum item is in the list and then remove and return it. Finding the minimum peak min is also going to require us to find where the minimum value is in the list. And then finally, isEmpty is just going to return true if the list is empty and false otherwise. So let's look at an example problem of some specific operation through an example problem with some priority queue operations. So first off, we have to get an instance of a priority queue. And in this case, we'll be using an unordered list of integers for our priority queue. So we will create a new unordered list object with integers as the type that it contains, and we'll store that in a pq variable, so for our priority queue. And then we'll do some operations. So let's start with an insert operation. So first off, we'll insert 247. So we'll go ahead and create our node, and we'll update our head and tail of our list appropriately. Next, we'll insert 1. So again, insert's just tacking on to the end of our list. So we'll add that to the end of our list. Next, we'll insert 131. So repeating the process of adding on to the end of our list. And now we'll insert 200. So at this point, we've inserted 4 nodes, and notice that they're not in any particular order. They're just in the order in which they were inserted. Next, we'll do our first extract min operation. So if this were a really long list, it wouldn't be obvious what the minimum value is. It's a really short list. We can just look at it visually and almost instantly pick out where the minimum value is. But of course, we'll have to implement this in code, and we'll have to have some programmatic way of identifying the minimum. So this is very similar to what we did in selection sort. We will iterate through our list. We'll start at the beginning. We'll identify the first value we come to as our candidate for the best overall. I'll keep track of the best overall with my black pen. And we move forward through the list. If the value we're currently on is better than the best we found so far, we'll update our notion of best and continue through our list until we hit the end. Okay, at this point, I have identified the best value overall in the list. So we will go ahead and extract it and return it. And our list will now contain just the 3 items, 247, 131, and 200. So our first call to extract min removed and returned to the number 1. Let's go ahead and do a couple more operations. So our next operation is peak min. So again, it may be obvious when we look at these 3 values what the minimum value is, but we have to find the answer programmatically. We have to start at our first value and assume it's our best overall, iterate through our list, and update our notion of the minimum overall as we iterate through our list. And in this case, it looks like 131 is the best value overall. So that's what peak min would return. And remember, this is just peaking. It's not actually extracting. So 131 stays in our list. So our next operation is going to insert -5. So this will just tack that onto the end of the list. And then we will extract the minimum. So again, our process of start at the beginning, identify that as the best overall, iterate through our list. As we come to better values, smaller values, we will update our notion of best. And when we're entirely done, we will have found the best overall. We will extract it and return it. One more operation, let's insert 100. So that will merely tack 100 onto the end of our list. And one more peak min, we'll iterate through our list, trying to find our best overall value. And once the best overall value has been found, it will return, but not extract, not remove that value. Okay, so let's summarize our implementation. So our insert operation was just tacking on to the end of a linked list, which is a constant time operation. Our extract min had to iterate through the entire list to find the min, so it was always taking n units of time if there were n items in the list. Likewise, peak min was also order n. And is empty is just checking to see if there is any node in the list, and if so, it is not empty. So that's also a constant time operation.